Good afternoon, participants. I am Pratima Pandey. So, first of all, what is a glacier? When we call glacier or when we say a glacier, what does it mean? So, as a definition, the glacier is a mass of moving glacier ice created by the accumulation of snow. As you can see from this picture, this is a field photograph of a glacier. You can see these fractures here. These fractures indicate that this huge mass of ice has got a movement. So a huge body of ice which has got a movement due to the topography can be called as a glacier. Any mass of ice which does not have any movement or any velocity won't be qualified to be called as a glacier. So for a glacier to define a glacier, movement is a crucial parameter. And where does it form? Wherever the average annual temperature is less than 0 degree for many years. So when the temperature will be less than 0 degree centigrade for suppose a lot of years, or suppose 10 years or 20 years, then there will be more snowfall than the melting, and this snowfall or the snow will accumulate. And over the years, when the accumulated snow, when its weight will be so high that it won't be able to hold itself, it will start moving following the topography. So that is how a glacier forms. So the condition, the basic condition for the formation of glacier is the temperature, which should be less than 0 degree centigrade. So this condition is fulfilled either at higher latitude or at higher altitude. So from this picture you can see the location of the glaciers in the world. So most of the glaciers are located in the mountains. Here you can see this is the Himalaya. Here you can see Alps. So these are the locations where the glaciers are located. And apart from mountain, the latitude, that means in the polar region. So these two regions, like the higher altitude and higher latitude, are the regions where we have more snow. The precipitation is more in the form of snow, and snow gets accumulated. So these are the regions where we have glaciers, polar regions and mountain region. So as they form in the polar regions or in the mountain, they are of two types: valley type or alpine or mountain glacier, and other type is the continental glacier, also known as the ice sheet. So the alpine glacier or generally mountain glacier, they are found in the mountain areas, and they are comparatively smaller than the ice sheets, and their length are greater than their width, and they cover only small portion. Also, they transform V-shaped valley into a U-shaped valley. As we go to the continental glacier, they form in relatively flat regions like Greenland, Antarctica, Alaska. These are the regions where we have mostly continental glaciers, and in the continental glacier, the glacier flow outward from the midpoint. This is a typical schematic picture of a mountain glacier. Since we are here, we have Himalaya, and most the glaciers in the Himalaya are mountain glaciers. So we'll talk mostly about the mountain glacier. So what is a mountain glacier? The glaciers which form in the valley of the mountain. So you can see this is a schematic picture of a mountain glacier, and this is a field photograph of a mountain glacier. So in a mountain glacier, we have accumulation zone and ablation zone. Accumulation zone is the upper part of the glacier. You can see this part. This is the accumulation zone. This is known as accumulation zone. Why? Because In this part of the glacier, we have snowfall. The precipitation is most in the form of snow, and snow gets accumulated to the glacier, increasing the mass of the glacier. So this is known as the accumulation zone. As we come down, the lower portion of the glacier is known as ablation zone, where we have seasonal snow. Say in the winter we have snow here, but in summer the snow gets melted away, or sublimation may also occur. So this is the ablation zone. The ablation zone is the zone of the glacier where the ice is mostly lost from the glacier. So we totally combine accumulation zone, ablation zone, and the mass gain and the mass loss gives us the mass balance of glaciers. This picture shows how a snow converts into glacial ice. In the precipitation we get snow. Snow converts into granular ice, and ice converts into firn, and then glacier ice. As they convert or as they transform, their density also changes from lower to higher. These are the field photographs showing the accumulation zone of the glacier. You can see these are the accumulation zone where we have only snow. There is nothing else except few crevasses. So we have accumulation zone, and this line, if you can see, this is the head wall crevasses. This is the head wall of the glacier, and the glacier starts from here below the head wall, and these are the crevasses known as Bergschule, from where the glacier starts. This is how an ablation zone looks like on the field. You can see this is the ablation zone, which are full of debris or the boulder. These are the, you can see the gray material here, these are the small boulders or the rock debris on the surface of the ablation zone of the glacier. And here the linear features, these are the supraglacial channels on the surface of the glacier. These are again few features on the surface of the ablation zone. This is supraglacial pond. This is the ablation zone of the glacier, fully covered with debris, and this is the pond. And this feature is a kind of well feature, like it is also known as the glacier well. You can see here, this is known as moleing. So most of the supraglacial channels, they discharge here. These are some of the landforms formed by glacier. Glacier also works as an agent, like water and air. It is also an agent which transform and form landforms on the surface of the earth. So one of the features found by glacier is the cirque. You can see this bowl shaped feature. This feature is known as cirque. This is a pyramid shaped feature, a peak. This is known as horn. A horn is a peak-like feature on the surface of the in the glaciated terrain, which can divide 3 or more than 3 cirques. This is a sharp knife-like ridge. This is known as the arid. And arid divides 2 cirques. So here should be 1 cirque, and here should be 1 cirque. These are again supraglacial ponds on the surface of the glacier. These are the proglacial lakes. We will further see about the lakes in subsequent slides. And this is crevasses. Crevasses on the surface of the glacier indicates that the glacier is moving and the glacier is very dynamic. These crevasses form due to the differential speed of the glacier. On the surface of the glacier, the velocity or the speed is not uniform throughout the glacier body. Somewhere, depending on the slope, somewhere the speed or the velocity will be high, and somewhere it will be not so high. So because of that difference in the speed at different parts of the glacier, these crevasses, they occur. Now how glacier and climate is related, we'll see. A glacier is known as the mirror or the reflector of climate. Whatever is occurring in the climate, it is immediately or with a response time will be reflected in the behavior of the glacier. Suppose we have a very good snowfall, we have a very good precipitation in terms of snowfall, then here in the accumulation zone, snow will be more and the accumulation zone will increase. Subsequently, abrasion zone will decrease. So we'll have a positive mass balance. So positive mass balance over the years, if we have positive mass balance, the glacier will subsequently advance. So if we have good environment in terms of glacier, that means we have not so very high temperature, we have very good snowfall, then over the years glacier will advance. In the reverse, if the climate is warm, then we have precipitation will be less in snow and more in rain. So we'll have the accumulation zone lesser than the ablation zone, and the mass balance of the glacier will be negative. Over the years, if we have negative mass balance, glacier will start retreating. So glacier mass balance and glacier advance and retreat, these are and the equilibrium line altitude which divides accumulation zone from ablation zone, these are the parameters which indicate the climate, change in climate through these parameters like accumulation zone, ablation zone, glacier, snout variation and equilibrium line altitude. By monitoring these parameters or studying this parameter, we can say what is occurring in the climate. Let us see what is the climate currently. So you know basically the temperature throughout the globe. You can feel also, and you have seen the trains also, that the temperature is in warming state. We are every year we are facing more and more heat, and here you can see this graph. This is also showing the trend of the temperature is rising. So this is the global status of the temperature. Coming to the Indian side, the observation has said this is the temperature of Indian landmass, the little yellowish color, and this dark color showing the temperature of Himalaya. So the study says that the temperature of overall India is rising, but the temperature, the rise in temperature in Himalaya is more than the Indian landmass. These are the temperature rise for Indian landmass, and here you can see these are the temperature rise in the Himalaya. So the temperature rise in Himalaya is more than the other parts of the India. Now coming to the Himalaya again, this is the situation. This is the rise or the trend of the temperature per decade at every altitude wise, at different altitudes. So these are the lower altitudes and these are the higher altitude. So here the picture or the graph plot shows that the rise of temperature is more in the upper altitude than the lower altitude. This is known as the elevation dependent warming. So the elevation dependent warming has been observed in Himalaya as well as in other mountain regions also. These are again the observation from western part of Himalaya. This is the global average temperature anomaly, and this is the western Himalayan temperature anomaly. So you can see the temperature anomaly in the Himalaya is almost double of the global average. That means here we are facing more warming than the global in the Himalaya. And also the situation of precipitation is that we are getting more rainfall. The rainfall, the precipitation in the form of rainfall is increasing, and the precipitation in the form of snowfall is decreasing. So because of the change in temperature, the precipitation is becoming more in the form of rainfall than in the snowfall. So we are getting lesser snow for our glaciers. So if since the climate is changing, we have seen from temperature and precipitation. So and we also saw that this climate change or any change in climate is reflected in the glacier. So if there will be any change in the glacier, it will affect other sectors also, like the sectors of land use, land cover, sea level will rise, water resources will be affected, hydropower energy sector will be affected, local climate will change, and it will also affect the ecosystem and biodiversity. So the change in glacier due to the change in climate won't remain constrained to itself, but it will also affect to the other domains. Now, in the response of this change in temperature and precipitation, it has been found that the most of the glaciers in Himalaya are retreating. So the glacier response here you can see, these are the example from various parts of the Himalaya. This picture is Gangotri Glacier. This is the Gangotri Glacier is one of the largest glacier of Uttarakhand in Himalaya. And if we monitor the snout of the glacier, we can see that the snout of the glacier has retreated for the Gangotri Glacier. So this was 1989, and in 2019 you can see the snout has come up to here. So this much frontal part of the glacier ice has lost. Now come to another glacier in Himachal Pradesh. This is Bada Shigri Glacier. This glacier has not only retreated, but also the tributary has got fragmented. So the glacier was here up to 1989. In 2017, the glacier has come here and this part has got fragmented. This is another glacier in Parvati Valley in Himachal Pradesh. This much part of this Parvati glacier has got lost because of the bombing. This is another glacier in Uttarakhand known as Shunkalpa Glacier. So the GSI, the Geological Survey of India, has stabilized the snout of the Shunkalpa Glacier in 1886 up to here. And if you monitor the glacier, the snout has come now here. So this much part the glacier has retreated. So glacier has come down to here from here. So this is the Samudra Tapu Glacier from Himachal Pradesh. This is also showing the retreating pattern. So these all examples shows that most of the glacier, except for few glaciers in Karakoram, many of the glaciers in Himalaya are retreating. So the retreat of the glacier are not only restricted for the snout change, but they are also causing to develop new lakes and expanding the already the lake which have formed already. So from this example you can see this is a Gepangad Glacier in Himachal Pradesh. There was a small lake here in 1989 and now the lake has started expanding and come up to the here in 2021. So the retreat of glacier, the fast melting of glacier is also causing glacier melt, faster melting of glacier are giving rise to glacier lake, development of glacier lake, formation of new glacier lakes and rapid expansion of glacier lake as you can see from this GIF. So this is the situation for Himalaya from various studies. So many studies have compiled the status of glaciers from various sectors of Himalaya, say East Himalaya, Central Himalaya, Western Himalaya and Karakoram Himalaya. So except for Karakoram, most of the glaciers in East Himalaya, Central Himalaya and Western Himalaya are retreating only. And this again shows the same thing, that the mass balance of the glaciers are also negative, and in response to the negative mass balance, the glaciers are retreating. So the future, the projection also shows the same thing, that if the carbon emission is, there are projection, as you know, many projections are there, basically which shows that if the carbon emissions are cut down, what will happen to temperature, and subsequently what will happen to the our glacier ice. So the projection says that if we cut down carbon emission very rapidly, so there would be a rise of 2.1 degrees centigrade in mountains in Himalaya, which again will be more than the global average, and in this scenario we will lose a third of ice by the year 2100. Again, the worst scenario would be if the carbon emission is less in regular basis, then the rise in Himalaya or in mountain will be 2.7 degree rise in temperature against the 2 degree centigrade rise in the global, and we will lose half of ice by the year 2100. If the carbon emission are not cut out, then the scenario is the temperature rise in Himalaya will be from 5 to 6 degree against the 4 to 5 degree as a global average, and we will lose 2/3 of ice by the year 2100. So this is the current situation where we are almost, the glaciers are retreating, and this is the future which shows the most of the ice will be lost. So coming to the indicator of glacier health, what are the parameters which indicates glacier health? One most important parameter is the glacier mass balance. Second is the glacier equilibrium line altitude or ELA, and also the glacier phases mapping. Then we have glacier area or the terminus position. Then we have glacier length, snow cover, glacier lakes, and glacier velocity. These are important parameters which we can study to monitor the health of the glacier. So if we use using remote sensing, what is the significance or what are the characteristics of remote sensing or the glaciers which are used for studying these parameters, the glacier parameters? So if there are two types of data set, you know, remote sensing data set, optical remote sensing and the SAR remote sensing. That means the microwave remote sensing. So optical remote sensing, where we get images in the visible region like a photograph. And optical remote sensing are said to be the workhorse for glacier related study, because here the glaciers can be studied very accurately through the visual interpretation. And what are the parameters? Mostly the reflectance or the spectral response curve from various parts of the glaciers, which helps to make it easier for us to study the glacier using remote sensing data. So this is the spectral response curve from various part of the glacier. This is from fresh snow. We all know that the snow has a very high albedo, 80 to 90%. So snow reflects almost all of the radiation coming to it. So this is the spectral response for the fresh snow. As the snow ages, the snow becomes fern. 1 year old snow is known as fern. So fern has a little lesser spectral response than the fresh snow. So the albedo or the reflectance of fern is lesser than fresh snow. The fern then becomes glacier ice, and the reflectance of glacier ice is lesser than the fern. So as the snow becomes glacier ice, the reflectance or the albedo also decreases. These are the debris covered glaciers. Also, they can also known as dirty glacier ice because they look like a brownish with the lots of debris on the surface of the glacier. So this is same you can see from this image. This is a satellite image of a particular glacier. So this is the fresh snow part, which is very bright because the albedo is very high. The reflectance is very high here. So this is the accumulation zone of the glacier. We have seen in field photograph that the accumulation zone is fully covered with snow. So it looks very bright because of the high albedo. This is accumulation zone. Then this part is the fawn part, a little older snow. So this has a little lesser albedo than this part. So fawn, you have seen this response curve. As we come to here, we have glacier ice, even lesser albedo, and these are the debris covered glacier, also known as the dirty ice. Here the spectral response curve or the albedo or the reflectance is even lesser, very less here. So this is how we can identify various parts of the glacier through in the remote sensing data or in the optical data. So using this type of image and the optical data, we can manually map the glacier. So we make FCC false color composite of images, and we can differentiate between glacier and the non-glacier bodies, and by mapping this way we can monitor the glacier. This is an example of the manual delineation of the glacier using remote sensing data. So you can see this is a Landsat image. On that the glacier has been manually digitized. So this is how we can delineate glacier manually using remote sensing data. And by using temporal data and manual delineation, we can, after mapping, we can monitor also. So this manual delineation method is very accurate because we can just see and monitor or delineate the glacier based on the visual interpretation. But if we have a very large area, like we have to monitor lots of glaciers, then this manual delineation will become very difficult. So in that case, we also can use a automated delineation method. So automated delineation method are the method where we use two contrasting bands. Two contrasting bands means, if you see from this curve, we have a very high reflectance, all the suppose snow, glacier ice, and fawn has high reflectance in the visible region, in the blue and green band. If we come to swire, there is a little dip here. This is the swire spectrum, the spectrum in the swire region. So using these two contrasting bands, we can do the band ratio. We can do this green divided by swire or blue divided by swire. This will help us in automatically delineating the glaciers. So using two contrasting bands, we can automatically delineate the glaciers. So what are the challenges in the mapping of the glacier using optical data? One is to identify the ice divide. What is ice divide? As you can see from this image, this is one glacier. This is accumulation zone, and the glacier is flowing from here to here. This is the upper part of the glacier and this is the lower part of the glacier. This is one glacier going this way and this is glacier 2 going this way. So from this optical image, 2D image, it is very difficult to know where is the starting point of glacier 1 and where is the starting point of glacier 2. They looks like merging here. So this is one of the challenge which we encounter while doing the glacier delineation. Then other challenge is the boundary of debris covered glacier. These are the debris covered glacier. So debris is basically the rock or boulder on the surface of the glacier, and they have a similar spectral response as the surrounding rocks. These are, the reddish color is the surrounding rocks, and here also have the similar spectrum. So it becomes very difficult to delineate the boundary of debris covered glacier. Then the third is the identifying the snout position of the glacier. Here sometimes it becomes difficult to identify where is the glacier ending and from where the water is starting, the discharge is starting. But many a times near the snout of the glacier we have lake, for example like this. So the existence of this type of lake, or sometimes the snout is more in the form of cave. So the shadow of that cave makes it easier to identify snout in the image. So these are the challenges which we encounter while doing the glacier mapping. So this is automatic delineation. Already we discussed that using two bands we can always do the band ratio and differentiate between glacier and snow and non-snow. Using the same technique, there is a term known as a normalized differential snow index, NDSI. NDSI can give you snow and non-snow. This is basically to differentiate or for doing the snow cover mapping and snow cover monitoring. So using NDSI, you can see this is the picture of glaciated portion, and when we apply NDSI, we get only the snow part. So using NDSI, we can do the snow cover mapping and snow cover monitoring. So using this NDSI, the satellite MODIS provides us snow cover data. So directly the snow cover product you can get from MODIS, and you can study the snow cover area analysis, for example like this. So this is the snow cover for January, Feb to December. So this is an example which shows how the snow cover product from MODIS data, which have used NDSI in its algorithm, can be used for the snow cover mapping and snow cover monitoring. The other technique for delineation is the supervised and unsupervised classification techniques. These are the two types of classification where we give training classes. So we choose many features here like glacier, snow, vegetation, barren areas. For each of the areas or each of the classes, we train our tool, a tool which can be in any software. We try to train those giving the training areas, and depending on our training areas and training sales, they gives us this type of result where we can easily delineate our features based on what we have given as to train the data. Now the most important parameter for the glacier health monitoring is mass balance. As we seen in the previous slides, mass balance is basically whatever input is there in the glacier in terms of snow and whatever output is from the glacier in terms of ice melt, and what remains to the glacier. So input minus output which remain to the glacier is the balance. Mass balance is the undelayed response of glacier to climate change. So by monitoring mass balance, we can directly understand what is going on in the climate. This mass balance can be measured by going on the field, doing the in situ measurement, or by hydrological method, or by remote sensing method. Going to the field and doing direct study is very difficult because most of the glaciers in Himalaya are located in the highly inaccessible areas. So going to the glacier, trekking to the glacier, and then doing study is a very difficult task. Like you can see, this is how the ablation is measured on the surface of the glacier. We put this bamboo on the surface of the ablation zone and keep on monitoring the exposed surface of the bamboo. Like we have put this bamboo this year, next year we'll go and we put marks also on these bamboos, and next year we'll go and we'll see how much surface of the bamboo is exposed. By that we can get to know how much ablation has occurred. This is how we measure ablation in the field. And this is how we measure accumulation in the field. So we do core and we take out the core and the snow parts and try to know through the density how much snow has accumulated this year. And by knowing how much snow has accumulated, we can get to know the accumulation. So this method are very difficult. So we have an alternative to in terms of remote sensing. So using remote sensing data, we can measure the mass balance also, change in mass balance. In that, what we do, we use digital elevation model, DEM. DEM gives us the surface elevation information. So if we have surface elevation information for 1 year and elevation information for another year, we do the differencing with some bias correction and we find the change in the elevation. We find the glacier surface elevation difference. We know the glacier area. Using glacier area and the change in elevation, we can estimate glacier volume, and using the density, we can convert it into the glacier mass change. So this is an example, how we can use remote sensing data for glacier mass balance estimation. This is an example from Gangotri Glacier. This is the Gangotri Glacier, and we have computed the change in the mass or change in the volume of the surface volume of the glacier through DEM of 2011 and DEM of 2013 using geodetic method. Another parameter is the glacier velocity. So by using two temporal data sets and by feature tracking method will track a feature on the surface of the glacier to find out the velocity. So by using remote sensing data, we can use feature tracking method to find out the displacement and subsequently glacier velocity. For example, this is example of glacier velocity. Here you can see these are the ice fall region where a lot of steepness is there, and in this steepness the velocity is supposed to be very high, and this shows from here also. Then we can also estimate the glacier depth. Glacier depth is basically using slope data and velocity data. We can estimate using empirical relation, we can estimate the depth of the glacier, and using temperature data like the Lancet, like the thermal data, the thermal band of remote sensing data can be used to estimate the surface temperature of the glacier. For example, you can see for this glacier the surface temperature has been estimated. This is the snout of the glacier, this is the ablation zone, and this is the accumulation zone of the glacier. So we can see in the accumulation zone the temperature is very low. If we come to the ablation zone, it is relatively high because of the debris here. We have debris mostly in the ablation zone. So the temperature of debris is more than the temperature of ice and snow. So this is how we can estimate the surface temperature. The other parameter of cryosphere is the permafrost mapping. Permafrost is one of the important parameter of cryosphere, which is defined as any surface which has a temperature less than 0 degree temperature or 0 degree Celsius for 2 consecutive years are known as the permafrost. So any ground having temperature less than 0 degree centigrade for 2 continuous years is known as permafrost or the frozen ground. So permafrost is very important to map because of 2 reasons. One, the thawing of permafrost because of the warming can destabilize the slope, because ice in the soil, they provide cohesiveness to the soil, and when the ice will melt out, the cohesiveness will lost and there will be chances for destabilization. So because of that also permafrost mapping is important. Secondly, this permafrost, the soil they contains lots of organic gases or the greenhouse gases like methane and carbon. So when the permafrost will melt, this soil will release methane, which is again a greenhouse gases. So this is why it is important to do the permafrost mapping. Again, other parameter for glacier monitoring or health monitoring is glacier lake mapping and glacier lake monitoring. As the glacier will retreat or will melt fast, our lakes or the size of the lake will also increase. So it is important to map and monitor the glacier lakes also, the high altitude glacier lakes also. So the glacier lake can be mapped again by using visual interpretation. Manually we can monitor the lake, or we can do the automated method like this NDWI. For W is here water in terms of normalized differential water index. Here we use near infrared and the blue band, two contrasting band to delineate water from or to differentiate water from other features. So using this you can easily differentiate from water bodies to non-water bodies. So this is how you can do the lake mapping. And lake mapping we do for lake inventory. Lake inventory is very important to understand how the lakes are growing, because the growing lakes or the expanding lakes can cause glacier hazards also, like glacier lake outburst flood. So to understand the glacier lake outburst flood, there is a need to monitor the lakes, and for monitoring we need to map the lake. So not all the lakes are hazardous. There are types of lakes which are prone for glacier lake outburst flood, vulnerable for glacier lake outburst flood, and there are stable lakes also. So depending on where the lakes are forming in terms of their mother glacier, it can be classified into proglacial lake, supraglacial lake, periglacial lake and cirque lake. Proglacial lakes are the lakes which formed in the front of the glacier like this. These are the proglacial lake. Many a times these lakes are bounded by moraines. So they are known as the moraine dam lakes. Then we have supraglacial lakes which are on the surface of the glacier. Then we have periglacial lakes which form in the periphery of the glacier. Then we have cirque lake which form in the depression. So this is the cirque lake. So it has been found cirque lakes are mostly stable lakes, and also supraglacial lakes are seasonal lakes. They form and they disappear. But the proglacial lake, moraine and proglacial lake, and this blocked lake and periglacial lakes are vulnerable for glacial lake outburst flood. So with using remote sensing data, we can do the lake inventory, which is the prerequisite for glacial lake outburst flood study. So in inventory, what we do, in inventory, we identify the lake, we assign the lake, the location of the lake, like coordinates, what is the dam type, what is the condition of the dam, what is the location of the lake with respect to the mother glacier. So they all parameters we assign and we call it glacier inventory. This is an example of the glacier lake inventory for Uttarakhand. So this is the state of Uttarakhand, and these are the upper parts of the Uttarakhand, the glaciated terrain of Uttarakhand, and using LIS4 data, which is a very good resolution Indian remote sensing satellite data, we have found that there are 1,353 glacier lakes in the Uttarakhand, and these lakes are every type, including all the types of lake like proglacial lake, supraglacial lake, periglacial lake, cirque lake. So there are 1,353 glacier lakes in Uttarakhand. So after we do the inventory of the glacier lake, now it is important to do the monitoring of glacier lake. Like if the glacier is, if the lake is expanding or it is stagnant. So for the GLOBE study, for the lake hazard study, one of the prerequisites is that the lake is expanding very fast. So for example, this is a lake in the Bilangna Valley in Uttarakhand near Kedarnath Valley. So this lake is expanding very fast. Here you see this is the lake image of 2016 and this is the lake image for 2020. So this much, almost 200 meter of ice has carved into the lake and the lake has increased. The size of the or the area of the lake has increased even in the 4 years. So using temporal remote sensing data, we can easily monitor the growth of the lake. So the main advantage of using remote sensing data for all the glaciological study is that it can cover a inaccessible terrain. Like it is always very safe to use remote sensing data and sit here and do all the glacier related analysis. You can find out glacier mass balance using remote sensing data. You can find out glacier volume change, glacier velocity, snow cover, how the snow cover is changing, how the equilibrium line is changing. So how if the glacier is retreating or advancing. By sitting here or without going in the field or in the inaccessible areas, very comfortably you can analyze and study the various parameters, and also it will provide you to do the based in how much scale you want to study. If you want to study a single glacier or if you want to study the whole basin or a regional scale. And if you are using radar data, it will also give you access throughout the years. Irrespective of cloud coverage, you will get information regarding the glacier surfaces or in the information. And also you can do other parameter studies, properties also. And also you can, based on models or based on temporal data, you can always go back and see what was there in the past through the archive data. So remote sensing overall will give you a lot of scope for studying glaciers, glacier related hazards and other parameters. So this is all from my side. Thank you so much.